Welcome to this webinar. In the next around 40 minutes, we will take a look at the debugging and tracing of the TRAVEO II microcontrollers from Infineon with our Universal Debug Engine, the UDE. I'll give you a getting started to UDE and I'll show you some basic debugging features and functions, and at the end we will also have a look at the trace capabilities, and I like to show you how to prepare the debugger and also the device to capture trace, especially program traces. Before we begin to look at the debug features and to look how to debug an application, let me introduce a little bit the TRAVEO II microcontroller. The TRAVEO II is a microcontroller that was added to Infineon's product portfolio of automotive microcontrollers after the acquisition of Cypress by Infineon in 2020. The family of the TRAVEO II is divided into main application domains. So there are addressed two main application domains in the automotive. On one side, there are body electronics, and on the other side, there are instrument clusters. For the software development and especially for debugging, we are looking primarily to the hardware architecture right now. When you look at the two pictures, you see the main cores. On the left picture, this is a body entry device of the TRAVEO II, which is based on Arm Cortex M4 as a main core. And on the right side, we see a body high device, which is based on a Cortex M7 core in a single core, or there are also dual core variants available. The same is for the cluster devices, where there are variants with Cortex M4 as well as single and dual Cortex M7 variants available. Besides the main CPU, or in the high device, the main CPUs with the dual core M7 or with the dual core M7s, there is always a Cortex M0 Plus integrated, which is for security, and we call them HSM, which is stands for Hardware Security Module. The hardware functions for debugging and also for tracing are based also on Arm IP. We have here the Arm CoreSight debug and trace technology in place. That means that the debugger can be connected either JTAG or SWD to the device using standardized connectors. These connectors are defined by Arm and present on all the evaluation boards. For the debug tool, the CoreSight subsystem provides, for example, hardware breakpoints and also triggers. These hardware breakpoints and triggers are used for providing basic debug functionalities in hardware, so that we can, from the debugger, use these capabilities for breaking the system, for providing single-step functionality, and also especially with the triggers for synchronizing the debug actions when we have multi-core configuration of the devices. So that are briefly the features that you get from TRAVEO II. These are the typical debugging features that you would expect. All the debugging features that you see here are available for the main CPUs, for the Cortex M4 or the M7 cores, and also for the Cortex M0 Plus, the HSM. Of course, we provide flash programming into the code flash and also into the work flash, and we have support for tracing. So for tracing, the UDE offers the option of recording the trace information in the on-chip trace buffer, the ETB, which is quite small, 8K. That's not too much, but you have also the option to transfer the traces off chip using a external parallel trace interface, and then you can store the trace information that you captured in the debugger hardware. For that, we have either the UAD2 Next in place, which provides you 512 megabyte trace memory, or if you need more, you can use our high-end UAD3 Plus device, which provides up to 4 gigabyte trace memory. The TRAVEO II is one of the latest additions in the device support in UDE. Therefore, it's only partially available in the current public version of the UDE, which is UDE 2023, and we released that version right after the embedded word in March this year. In the pre-release of the UDE, which we call UDE 2024, which will be public next year, there are all the available devices of the TRAVEO II family supported. If you have projects with these devices, which based on Cortex M7 single core or dual core variants, then of course you can ask for that version and we will provide it to you. Okay, then let's have a look before we go to the debug tool. Let's have a look to the software development in general. So how a software partitioning in the TRAVEO looks like. So basically there are two boot configurations here possible in the TRAVEO II. The typical boot configuration is multi-core, and then you can configure the device also to be or to act like a single core system. In the multi-core configuration, it is always the case that at first the Cortex M0 Plus or the HSM core is booted and the application there is launched. And then this HSM application starts after that the main CPU application that is running on the M4 or the M7 cores. If you have configured the TRAVEO to be a single core device, then only the main core, or in the case of a dual core configuration, the main cores are started, and there is no HSM involved anymore. As a result of that, we have basically three different types of software partitioning. The first one is heterogeneous partitioning, where we have two binaries here seen on the left side. Two binaries. First binary is for the HSM, and the second binary for the main cores or the main core. Then of course we can have completely separate ELF files here or binaries for all the cores in this I call it independent applications partitioning. And finally, if we have only a single core configuration, that we have a single application that is running on the main cores, the Cortex M4 or the M7s. These different software architectures also result in different requirements for debugging. Either we need a fully synchronized debugging where all the cores stop when debugger reaches a breakpoint. And then we have a partitionally synchronized debugging. That is if only I want to stop the main core or the main cores, and the HSM should keep running. And finally, you can also have a completely unsynchronized debugging. So breaking and single stepping are only performed on only one core, and the other cores remain untouched. Okay, before we go to the debugger and before I show you some basics and how to get started with debugging the TRAVEO II, a few words about the hardware setup. This is a typical hardware setup for debugging a TRAVEO II. So we use for the demo, I use a evaluation board with a smaller device, which contains only a Cortex M4 and the HSM. But for the bigger devices with the M7s, it's quite the same look and feel, and also the behavior of the debug tool or how to use it. This picture shows the simplest hardware setup for debugging. It's not actually that what I am using in the demo right now. You will see a picture later of that, but it is the typical setup for debugging without tracing. We use a UAD2 Pro here, which is one of our devices of the Universal Access device family. It's the basic device, the smallest one. The UAD2 Pro is connected using USB. See it here on the left side to the Windows PC where the debugger software is running. And to connect to the evaluation board, the debugger, we use the standard Arm JTAG and SWD debug adapter. Here you see there are some connectors here available for the different types of connectors that we have on ARM-based devices. By the way, this adapter is the only target-specific part in the debugger hardware setup. The UAD2 Pro, as well as all of our other devices, are universal. That means you can use them also for other architectures or other devices like the AURIX or something else. The only thing you need to change is the matching or the adapter that should match to the target system, and you need, of course, a architecture license that you can use UDE with a different type of microcontroller architecture. Okay, and then let's jump to the debug tool, and yeah, let's create a workspace. A workspace is basically the term that I use for a debug session. So if you want to debug a system, then you have to open or you have to create a workspace in UDE, and that's quite simple. You have the possibility to use either the toolbar here or with some icons there or buttons there, or if you like, you can use the menu as well. So all the functions of UDE are either available by icons here in the toolbar or in the function. I use the function, the function menu. Create new workspace, quite simple. Click on new workspace. Then you get a file open dialog or create a dialog. There is already a name given here. That is because I have prepared that demonstration right before, but I can reuse this name or I use a new one. Then UDE asks for a so-called target configuration. That means UDE should know which target should be connected or which type of microcontroller should be connected, how it should be connected, which debug interface should be used, and some other settings as well. There may be a target configuration already present here from other projects in your company, from teammates or something like that. You can look for some target configurations in your computer, but if you start from scratch, then I recommend to use the default button where you get a complete list of predefined target configurations for all the available or all the supported microcontroller architectures and also for all the available evaluation boards. If you look here, you see some Cortex-based devices, and the TRAVEO is somewhere here. I open it, and then we find the board that is connected to my UAD on the desktop. I press finished, and then I save that target configuration file somewhere. I take the location here to keep it simple. Okay. You can also use such a predefined target configuration if you have a custom board. Then you can change some settings later on to adapt the target configuration to your specific needs if you have a customized board or some end product, for example. Okay. Then we select the save target configuration, press OK, and then the debugger asks you which cores you want to see in the debugger. We want to see both cores. We have a Cortex M0 Plus here, the HSM, and the Cortex M4 core as a main core. So we leave this untouched. This is this default configuration. Press OK, and then we get a connected UDE. So we see here in the message box there are some information here available, and also that we have a successful connection to both cores of that TRAVEO II board on my desktop. Both cores are visible in one user interface. That is a key feature of UDE. So multi-core systems are present in one user interface. You see here on top in the toolbar the status of both cores, and also you can use the toolbar to switch between the both cores for focusing on one of those cores if you, for example, want to look into registers, into variables, into source code, etc. Which core is active right now? You see on the status bar on bottom here. Okay, what we need is a application that should be loaded into the system. I use the menu again. You can also access this using the toolbar. Load program. And I told you that in the multi-core configuration, we need two applications. One is booting up and it's executed by the HSM, and one application that do the rest, which is executed on the main core. So the first thing I'd like to do is loading the boot application. I have a simple one prepared for programming into the Flash. We can load hex files, we can load ELF files here. I take for that example the hex file here. The hex file contains only the binaries. That means the content is completely written to the flash of the HSM in that case. You see here we have two checkbox types. We have blue ones and green ones. and the blue one is for telling the debugger which core should flash which application, and the green one says or tells the debugger which debug information out of the ELF file should be loaded to which core debugger in the debug tool in the UDE. So because we have a hex file without any debug information, pure binaries, we have grayed out the simple information here or the debug information, but I'd like to see debug information in the debug tool that are links to the source files, which functions are defined, which variables are present, and something else. And for that, I have here the option to check the hex ELF, which enables then the support for symbols and automatically loads the ELF file, which has the same name as the hex file has. If there's a different name for the ELF file, then you will be asked for loading the ELF file. But in this case, we have the same name, everything is okay. The debug information in this ELF file for the time demo.hex is only for the HSM, so I untick the Cortex M4 symbol loading. And then we need the main application. I go back to my folder here and browse in the ELF file, for example. And this ELF file should also be loaded into the flash. And in this configuration, the flash handling is done by the HSM. So don't tick the Cortex M4 core for flash programming, tick the HSM, and then load the symbols to the Cortex M4 debugger in the UDE. Okay, that's all. Now we can press OK. Then we will be asked perhaps to provide some of the source files. This happens always if you build your application or your code not on, for example, on that PC or on the place where the ELF file is located, somewhere else, for example. The ELF file contains the paths to the source files, but this may be not correct anymore. In my specific case, I copied the application to that PC. Now you can look for the source files, but we can skip this for the moment. I show you a workaround right now in a minute how to solve this. So I cancel every request here, and then the flash tool gets opened, and then I can program all, and both applications are right now flashed into my target system. Okay, we want to see the source files. We have skipped the opening requests of UDE, and I'd like to show you how to manage the case where source files not found at a place where they should be found based on the ELF file information. In the menu config, we have a debug server configuration, which is basically the central point for setting all the debugger related stuff. And here we have on the left side a list or a tree of categories, and we open the view server category source code. And here we have two buttons. The right button, aliases, shows us all the source files which we skipped right before, and this should be deleted. And then we can define a path replacement by pressing path management button, and then we get this dialog here where we can use this button to define a path replacement. On top, in the top line, we browse in the path which is given to the source files from the ELF file. Here, these four are of interest. We take this one. We can remove the trailing path element here in that specific case to make it a little bit simpler. And then I open in the second line here the browser and browse for the Cortex M0 folder where all the source files are located for the Cortex M0. Press OK, and the same I do for the M4. I can also delete the trailing path element and then define the path replacement for the M4 core. Okay, I close it, and then I can go to my simple browser on the left side, press here, double click on main, then the main source file with the main function timedemo.c is opened. I put it on the right side, and then also for the HSM I can open the folder, the file, and then I can look and not start debugging. There is some specific that maybe happen in such a configuration. If you look at the count position of our program counter after reset or on reset, and then we see here that is not the start address of our application. It is somewhere in the reset handler. That may happen either, and it's the case here, if the ELF file contains not exact information, or in the case where, for example, you have already flashed a boot code into the HSM flash, and then also sometimes wrong information is provided to set the start address. But don't worry, there is an option in UDE to change that behavior. Make sure that you are in the HSM, and then you can use the menu config target interface entry here, which opens that box, which has a lot of settings here to change the behavior, how the target is connected, and also reset behavior and something like that. And on the tab Cortex M, there is an option, use hardware start mode. And if we press or if we enable this, then the normal mechanism to set the startup program counter to the start address of the loaded program is disabled. If you check this box, then the UDE reads instead the vector table offset register and sets then the program counter as well as also the link register stack pointer accordingly to the right values. Okay, then we have to reset the system. And if the reset is done, we see, okay, we have now our start address is here at this address, and this should be fine. Okay, and then we start the application. We see on top here, both cores are running. You see not much. That's why I open for both cores the watch window, browse in some variables. We have a seconds count. It's a simple timer here, and we have also a counter which should count up. Then I can enable periodic refresh, that we see the values changing during runtime. and the same I do for the Cortex M4 core. Click here on that on this toolbar element. Open the watch window for the Cortex M4 core. You see the color here. Browse for the variables. This is quite the same application with the same variables, but these are not in fact the same locations. Okay, and then set periodic refresh. So same variable names on both cores, but not the same locations here. If you look at the addresses here, we see it is something 2014 at the end, and here's something with 20 OC. Okay, it's not the same not the same value. We will see it later on. Then the differences. Okay, then we can start debugging, setting, for example, a breakpoint. I open breakpoint window to have it listed. And then I can, for example, go to the Cortex M4 core. Let's go to the demo function 2 and set a breakpoint here by clicking on the blue bubble here on the left side. And then instantly the breakpoint is hit. We see where we are in the code, and we see at the same time that also the core, the HSM has stopped. And this is the default behavior of UDE when you have a multi-core system. We have two cores here. Both are synchronized for run control. That means breaking and also single stepping. When you single step, for example, here in the main core, then we will see after a while that we do also a kind of single step. It's not exactly a single step here on the HSM core. Well, we are okay. Now it is something changing here. Yes, okay. If you lose this, the focus here, then you can press the yellow arrow here. But you see, okay, both cores are synchronized. That is good for some application, that may not so good for other applications, and that's why you have the possibility to change that behavior. To change that behavior, there's a limitation. This can also only be done if the complete system is stopped. That's why, then you can change this. In the menu config, you get the multi-core run control configuration, which contains so-called run control groups or one run control group. Here in this run control group, only the possible, it's only possible to have two cores here because we have only two cores available on that device. And you see, okay, both cores are part of the run control group. And that means they are synchronized. I can disable this very easily by untick this checkbox, and then I disable the breakpoint, and then we have a unsynchronized behavior for debugging. I can start my main application. You see the main application is running, and then I can start also the HSM. The HSM is running, and if I enable the breakpoint again, we stop only in the main application or the main core. The HSM remains running. Okay, to bring that back to the synchronized mode, you have to manually stop also the HSM. Then I can open the run control management again, check that box, and then I can start the application. Both cores are running right now. They are synchronized. If I enable the breakpoint again, then both cores are synchronized for debugging. Okay, That's basically how to debug the multi-core system. Then, of course, you can look at the registers. You can, for example, at a breakpoint, look into the core stack. You can look at the locals, for example, to see the values that are local to the function. And you can also look into the peripheral registers that are quite important if you want to debug or test a embedded system. For example, we can look at all the registers that are present for all the modules in the device. For example, we can have a look at some of the timer registers. For example, this timer is used here in the application. I can add some of the registers and I can also change. This is not the can also enable the periodic refresh. Then you see the timer value counting up. We can change the format here, for example, decimal, change that value to maybe 4000. And then if I reload the timer, then you see our seconds are incremented 10 times faster, which is not okay. Okay. I need a bit hurry up because of the time. The next, what I have to, or what I want to talk about is how to use trace for the TRAVEO II. So I said before, we have a Cortex, a CoreSight debug and trace system implemented here. This provides, especially for the TRAVEO II, a ARM embedded trace macro cell that allows you to do program trace. It's called ETM. And we have also an instrumentation macro cell, ITM, for instrumentation trace. So the instrumentation trace is somehow similar to printf debugging. However, instead of that printf function, which has a lot of overhead, you can basically write application values to dedicated so-called stimulus ports in the ITM, and these values are then output to as a trace message to the trace stream. As already mentioned, the recorded trace messages can be stored in a on-chip trace buffer, the ETB, or you can transfer them off-chip using a parallel trace interface. So you know, the ETB has only 8K memory, which would result in very short trace runs. But with the trace option, using the trace port interface, you can connect our UAD to Next to trace into this trace memory which has 512 megabyte. So significantly longer trace recordings are possible. To use the external trace option from the debugger hardware side, you will need the UAD to Next, of course, and an additional trace module that can be plugged in, shown here on this picture. And we need also a trace adapter. On the target side, we need to define or to configure the target pins to provide the trace output. This configuration is already prepared in the target configuration of UDE, but not enabled. So you have to enable that, and I'd like to show that in a few seconds. That is the actual setup that I have on my desk. So you see DoD to next device with the parallel trace module plugged in front of the device. For debugging, we need the Arm JTAG SWD adapter here, and also the trace adapter for CoreSight trace. And this is connected using this 20-pin flat ribbon cable to the connector on the board here. The UD to Next can be connected using USB to the PC, USB 3, or if you like, you can put it in your network and access the device using Ethernet. Okay, and then finally, let's have a look at the trace. I said before we have to enable the external trace. That can be done by also the target interface setup for the Cortex, for the HSM core, of course. We have in the Connect tab here so-called init commands for the connect process, and here we have prepared the configuration of the hardware pins for the trace output, which are commanded at the moment. So to enable the external trace, simply uncommand all the set commands here, press OK, and then we can reset the target system. And then we open the trace window here for the CoreSight system. I put it out. It's not the right window. I'd like to have that one. And then we can configure the trace. In the General tab, we switch from ETB to the parallel trace of the UAD2Next. And then we can specify the memory size, for example, 4 megabyte here, that the trace will not be too huge because more trace needs more time to analyze. We want to see some timings information here, and we want to start the trace on a certain condition. So this is basically the setup for the trigger where the trace has to be, when the trace has to be started or stopped. In this pre-trigger configuration, we wait, or the trace system waits for a condition and then starts the trace recording. In the post-trigger condition, everything is traced right before a condition, and then the trace is stopped, basically spoken. Okay, trigger position on the position here, and then we enable the code trace for the Cortex M4. We want to see some timestamps, and we need the trigger condition, basically a code address, for example, update wave buffer. And then we can close that, start trace recording, and nothing happens right now. Maybe I have to restart, reconnect because of the settings of the trace port. And then we start the application, of course, and start the trace again. And then here we are. We have the trace recording. You see in a list view the executed machine code instructions, executed instructions on source code level, and also which function. But this is not a very nice view. You can look at the execution sequence also in another window, which we call execution sequence chart, which provides you a nice view to the execution sequence of the functions here, or if you have an operating system in place, also for the tasks. it takes some seconds to be analyzed. Here you see we are almost done, and then we can unfold that and look into the time range, and then we can zoom in and zoom out, and you see the execution sequence of all the functions. It's nothing unusual here for that simple application. Okay, with that, the time is up for today's webinar. Thank you very much.